Problem 1529. We have three charges here arranged in an interesting way. Each of the three charges are 2 meters from the origin. In fact, the author has a circle drawn showing that they're all on a circle of 2-meter radius. The first charge here is at an angle of 30 degrees from the x-axis. The author says the second charge is at an angle of 150 degrees from the x-axis, which works out to 30 degrees above the negative x-axis. And the last charge is located at an angle of 270 degrees, which puts it on the negative y-axis. He wants to know what is the electric field at the origin. Now there are three charges producing an effect. So to get the total electric field, we'll need to find the field from each and then sum them together, keeping in mind that they are vectors, so we can't just add the magnitudes. If I call this one number 1, that one number 2, and this one number 3, we'll just have to work out the contributions from each. So let's try number 1 first. Starting with magnitude, that would be K times Q. Again, I'm just finding the magnitude here, so I don't need to worry about the fact that this is actually a negative charge. We'll come back and get the direction once we've got the magnitude. Divide by r squared, which works out to be 4, and that gives a magnitude of electric field 1.124 times 10 to the 4th newtons per coulomb. Now, what's the direction? Okay, right here at the origin, the rule is that the electric field points away from positive charges, but this one's negative, and towards negative charges. So if I'm at the origin, towards this one is up and to the right at an angle of 30 degrees. So that means this electric field has a positive x component and a positive y component. That would be 1.124 times 10 to the 4th cosine of 30i for the x component, plus 1.124 times 10 to the 4th sine of 30j for the y component, which works out to 9.732 times 10 to the 3rd I plus 5.619 times 10 to the 3rd j. So there is the first contribution to the electric field from charge number 1. Alright, just 2 more to go. E2 is K times Q divided by R squared, which are all exactly the same numbers as this one. So actually I don't need to do it again, that's going to be the same magnitude, 1.124 times 10 to the 4th. But we do need the direction. At the origin, the electric field points towards a negative source. Number 2 is negative, so it will point that way, to the left, and up 30 degrees. So the x component is negative, and the y component is positive. The angle is the same as for this one, so I guess I could just write it down. Minus 9.732 times 10 to the 3rd I plus 5.619 times 10 to the 3 j newtons per coulomb. So there's the second contribution. One last one to go. Number 3. Well, this is the same amount of charge, it's the same distance to the origin, so that will have the same magnitude. But what's the direction? Okay, if I'm at the origin, the electric field from this charge number 3 will point towards it since it is negative. So that electric field will be straight down along the negative y direction, represented by a minus j. So this electric field with direction is minus 1.124 times 10 to the 4th j newtons per coulomb. There's the last contribution. Now all I have to do is add these together. Let me see if I can add them over here. I'll just put E1, 9.732 times 10 to the 3rd I plus 5.619 times 10 to the 3 j. And then plus, let me add the second one, minus 9.732 times 10 to the third I plus 5.619 times 10 to the 3j. And then the last one here has no x component, but the y component is minus 1.124 times 10 to the third j. If I add these up, the two x components give you 0. And if you add these two, you get 1.124 times 10 to the third, and then you subtract, and you get 0j. So in fact, at the origin, the electric field is 0. If I were to put a positive charge right there at the origin, it would experience no net force. If you were to tap it just a little bit off to one side, then the force of whichever charge is closer would be a little bigger, and it would then accelerate away from the middle. But right at the center, it's in equilibrium, no net force. Unstable equilibrium, but still equilibrium nonetheless.